Okay, this is where we are from yesterday's discussion of vector graph. This is the most interesting case of use of vector graph for decoding. We see that we have a block. Remember, every block in a vector graph represents a function, and the function here is the Iverson function of the statement x belonging to C. So this is a function taking value 1 if x is a code word, and taking value 0 if x is not a code word. And this block here represent the memberless channel, and consequently these functional blocks represent these functions p of y sub I given x sub I. Remember that these are functions of x sub I alone, and y sub I is what we observe at the output of the channel. So if we want to do decoding, soft decoding using the sum product algorithm, which is the first step to do maximum a posteriori decoding, we should apply the sum product algorithm to this vector graph. Okay? And these are the two steps of the procedure. We first compute these functions that depend on our knowledge of the channel, I, that are messages going upward, and then we need the message going downward. Remember that the product of the two messages in the two directions associated with each edge provide us with the marginal, that is with the a posteriori probability of each one of the symbols. And the critical calculation is, the more complex calculation is the calculation of E of x sub I, because this involves the evaluation of the Iverson function of x belonging to C. It's not practical, of course, to compute the Iverson function with a brute force approach, because what we have to do is to consider all the values of the components of x and look in a code book to see if x is a code word or not. So we need to take a closer look at the structure of this block. In particular, we would like to factor also this Iverson function according to the structure of the code. Once we have done this, we have simplified, we have maximum simplification of the vector graph, and consequently we can do our decoding in the most efficient way. Okay, tenor graph is exactly this, does exactly this. Tenor graph are vector graphs that describe the factorization of the function. So we can explode the big function representing the code into a number of smaller blocks. So let's look at what the tenor graph is. Very simple. The concept of tenor graph is very simple, especially when you consider some linear binary code. Remember that a linear binary code can be represented by its parity check matrix. Parity check matrix simply describes the constraints that the symbols of the code word must satisfy in order to be to generate a code word. So the first row of H that has 1 in column 1, 2, and 3 simply expresses the fact that the sum, the modulo 2 sum of the first 3 components of the vector must be equal to 0. Second row has a 1 in position 1, 4, and 5, and consequently the sum x1 plus x4 plus 5 must be equal to 0, and similarly for the third row. Consequently, these are the constraints that must be satisfied. A code word, a vector, a binary 7-tuple, is a code word if and only if these 3 constraints are satisfied. Consequently, saying that x belongs to C is tantamount to saying that this constraint is satisfied, and this is satisfied, and this is satisfied. And hence, the Iverson function of the statement x is a code word can be split as a product of 3 Iverson functions, each one representing one of the constraints. Okay, so this is what we have in terms of vector graph. This is not in the normal form, but anyway, it's a vector graph that expresses what we have here. This block, this functional block, simply is a function that takes value 1 if the sum of the arguments is 0, modulo 2 sum is 0. Consequently, this block represents the Iverson function of x1 plus x2 plus x3 equal to 0, and so forth for the other. So it's very simple to generate a vector graph. So we have a vector graph here that represent this code. Once we have the code represented in the form of a parity check matrix, we immediately have the tenor graph, which comes out from the factorization of the Iverson function. And consequently, we could take this tenor graph and substitute it in this big functional block. You see the functional block that has input or output x1, x2, and xn, and these are the represented by these half edges in the tenor graph. You see that in this case the tenor graph has no cycle, and consequently if we decode this code using the sum product algorithm, we don't have the need of any iterative algorithm. We can do it in a finite number of steps. In some other cases, the tenor graph has cycles, and unfortunately we have to resort to an iterative algorithm for decoding. But let me show you a very simple example of self-decoding using the sum product algorithm in a code that has whose factor graph has no cycle. This is the 322 single parity check code described by a single constraint, x1 plus x2 plus x3 equal to 0. So the blue area, the blue shaded area, represent the block of an Iverson function. X is a code word. Okay, so we splice this block to the blocks representing the channel, and this is what we have. Okay, now let me tell you, using this simple example, why the messages, as we have seen before, the messages going upward are called I, intrinsic, and the messages going downward are called E, extrinsic. We can see it very simply using this factor graph. Let's focus on the marginal of first component, x1. So the message coming from here comes from our observation of the output of the channel corresponding to the first component. We call it intrinsic. Okay? This comes only from the observation of y1 once x1 has been transmitted. The other messages go in the opposite direction, whose product with the intrinsic messages will give us the a posteriori probability of symbol x1, comes from the following observation. It comes from the observation of y2 and y3, that is the output of the channel corresponding to the other two components of the code word, and our knowledge of the structure of the code. Okay? So we have an intrinsic message coming from the observation of the corresponding output of the channel, and the extrinsic observation comes from the combination of the structure of the code and the observation of the other components. This is the information that is provided about x1 by the observation of y2 and y3 and our knowledge of the code. This is why it is called an extrinsic. Okay, so this is what we had to do. I mean, the messages, the output of these blocks are simply the values of these functions, and the messages at the inputs of this block are simply the extrinsic messages that can be computed by one single step of the sum product algorithm, according to the recipe that we have seen yesterday in the afternoon. So that's it. Unfortunately, there is a folk theorem that says that good codes have loops. And consequently, we cannot expect that in a practical case when we want a good code, we can use the sum product algorithm without iteration. This is an example of a tenor graph corresponding to a code that generates cycles. This is a Hamming code, which is expected to be good. And the constraints described in the code are these three, and consequently we can factor the Iverson function of the statement x is a code word as a product of three terms, and we have this structure. We see that we have loops here. Remember that to be able to use in efficient way an iterative or turbo algorithm on a factor graph, the loops must be big enough. So we cannot expect to have a good convergence properties if we use an iterative algorithm on a code like this, simply because the girth of the graph is very small. To have efficiency, to have a code that can be efficiently decoded using iterative algorithm, we need big loops, and consequently we need a large number of variables. So we need block lengths that are considerably large. And in fact, this theory is successful for code like the low-density parity check code. This is an example of a it's called regular low-density parity check code. The structure is exactly, in terms of factor graph, the structure can be understood by just looking at this picture. What we have, these are the variables, these are the symbols, okay? The symbols are broadcast, this is a repetition node, are broadcast to this block pi, it's a permutation or an interleaver. And the output of interleaver, we collect the symbols and we send them to a parity check node. So this is the structure of a low-density parity check code. What characterizes a low-density parity check code is simply the number of edges at the output of each one of these repetition nodes, the output of the edges at the input of each one of these parity check nodes, and the structure of the permutation. Once we define this number, and the structure of the permutation, we have designed a low-density parity check code. And I'll show you in a few minutes how we can apply the sum product algorithm in iterative form in order to decode the low-density parity check code. Okay, so this is a tenor graph. What happens if instead of having a black code, linear binary black code represented by its parity check metric, we have a code represented by a trellis, let's say a convolutional code or something. Okay, so we had to extend a tenor graph, to generalize tenor graph to this situation. Let's suppose that we have a code represented by a trellis, and let's consider one section of the trellis. For example, this section in which we have 2 initial states and 4 ending states for this section of the trellis, and A, B are the labels of the branches. So this may be a convolutional code, or maybe a trellis-coded modulation scheme, etc. And this is the initial state at time I-1, and this is the state at time I. How can we describe mathematically this section of the trellis? In this way. Each branch, its transition from one state to the next, is described by the initial state, the state sigma I-1, the ending state sigma I, and the label. Okay? So we may say that this section of the trellis is represented by the set of transition from 0 to 0 driven by symbol A, from 0 to 2 driven by symbol B, etc. That's it. So we can represent every section of a trellis by saying a transition is between one state to the next is an allowable transition if it belongs to a certain set. Okay, so from this it's easy to derive the Iverson function representing the section of the trellis. So we say that the section of the trellis is represented by a functional block that simply Iverson function saying the transition from state I-1 to state I driven by symbol x sub I is a element of the set T sub I. And this is driven by symbol x sub I. So this is a block, functional block that represents a section of the trellis. Very general, so any trellis can be represented in this way. And consequently, if we have a trellis code, we have a vector graph having this form, which we simply take the trellis, we consider it section by section, we define the Iverson function associated with each section of the trellis, and we align these blocks in the vector graph. One might observe immediately that the following. Each code can be represented by a trellis. Each code represented by a trellis can be represented by a vector graph that has no loops. This has no loops. That means that every code can be decoded in a finite number of steps using the sum product algorithm. No need of iterative algorithm. That's true, but if we, for example, if we have a turbo code and we want to represent it as a trellis code and consequently by a vector graph that has no loops, we discover immediately that the complexity of the calculation involved in each one of these nodes may be too large. Actually, the complexity of the calculation involved by these nodes depend on the number of states in the trellis. For turbo code, for example, we have a huge number of states, and consequently, it becomes impractical to decode a turbo code without iterative algorithm. Right? So there is a compromise that, of course, has to be studied before deciding which decoding algorithm we want to choose, between the complexity of a single calculation, if we want to use a finite algorithm, versus the complexity of a single calculation if we want to use an iterative algorithm. Right. Iterative algorithm requires many simple calculations. This structure of vector graph requires a lower number of calculations, but each calculation may be more complex. Okay, this is a couple of examples of a tenor graph of codes represented by trellis. This is repetition code. Remember, this block simply says that all the input take the same value. So this is a repetition code with block length 4. So the value may be either 0 for all 4 components or 1 for all 4 components. And we have seen yesterday that the repetition code can be represented by this trellis with only 2 paths, the all 0 path and the all 1 path, corresponding to the 2 code words that we have. And we can represent this in the form of a linear tenor graph that corresponds exactly to the structure. Similarly, if we have a single parity check code, this is the standard tenor graph, and this is the tenor graph corresponding to the trellis representation of the code. Well, in this case, in the previous case, it's obvious that the two are the same. In some other cases, things may be more complex, like this one. This is an 844 read mother code, and we can represent this in the form of a vector graph like this. And of course, the structure of the Iverson function describing this function may be more complex than in the previous case. But anyway, this is obviously doable. Remember also that to use efficiently an iterative algorithm, we need big loops, and consequently for short codes we cannot efficiently use an iterative algorithm. So for example, if we want to do maximum a posteriori decoding of this code, this is the structure that we should use. Now, turbo codes. This is the simplest and yet the most efficient version of a turbo code. They work like this. We have a sequence of raw data coming from the source. We call them U. We send them over the channel without any coding. Then we send the same sequence of symbols to a convolutional encoder, to a systematic convolutional encoder, so that the first part of the code word consists of U and the second part consists of a parity check symbol. We disregard the first part and we only send to the channel the parity check symbol of this convolutional encoder. Then we take one more time U, we pass the U through a permutation, an interleaver. We get the scrambled version of the symbols U. We send them through another convolutional encoder, which may be equal to the first one. And we do the same. We take the parity check symbol and we send this to the channel. Okay, so this turbo code can be represented by a vector graph like this. This is the structure of a vector graph of a turbo code. This U represents the symbol that we receive from the source. U are broadcast on the left part and on the right part. On the left part, they go through a convolutional encoder that is represented by the linear vector graph. Also, they are also sent to a permutation that changes the order of the symbols, and the output of the permutation is sent to another convolutional encoder. That's it. So we have P, U, and Q, and this expresses the structure of the turbo code in the form of a tenor graph. And this structure is useful because by looking at the graphical structure we can design an iterative algorithm, as I will show you in a few minutes. Another possibility is to use a tail-byte encode. Remember, a tail-byte encode may be very efficient because if we look at the number of states of a standard trellis representation and at the number of states of the corresponding tail-byting representation, that is a trellis such that the initial state and the final state coincide, right? We may discover that the number of states in the tail-byting version of the code might be much smaller than the original version, square root of the original version typically. So if we can use a tail-byting version of a code, that could be a simplification, considerable simplification in terms of the decoding complexity. You might be familiar with the BCJR algorithm, Balcock, Jelinek, and Raviv algorithm. We may discover that in a very easy way that the BCJR algorithm is just the sum product algorithm applied to the linear version of the vector graph. No more, no less. So if we apply the sum product algorithm to that structure, we have exactly the BCJR algorithm. And it's interesting, if you ever have the chance of looking through my book, I have derived the BCJR algorithm in the standard way, in the historically original way, and using the sum product algorithm. Well, the first derivation takes 3 pages, the second derivation takes 3 lines, which means that once you have understood the sum product algorithm, which is conceptually very simple, as we have seen, then you have a possibility of understanding a number of other algorithms that are apparently more complex. Actually, the original version of BCJR looks more complex, but interpreted as a sum product algorithm becomes really simple. Okay, this again a low-density parity check code. In the low-density parity check code, typically the tenor graph has cycles, so we are interested in decoding low-density parity check code by using an iterative algorithm. That is the iterative version of the sum product algorithm. We know the basic step of the sum product algorithm, you know, what kind of calculation we have to perform. We need a schedule. I mean, we have to schedule our calculations. This is an example of a low-density parity check code, regular low-density parity check code described through the parity check matrix. What characterizes a low-density parity check code is the regular low-density parity check code is the fact that each row of the matrix H and each column of the matrix A contain the same number of ones. So in this case, we have 4 ones in each row and 3 ones in each column. Represented in terms of a tenor graph, we have WC edges at the output of each one of these repetition nodes, and WC is the weight of the column, the number of ones in each column, and WR, the number of edges entering this parity check nodes, is equal to the number of ones in the row. So this weight, column weight, and row weight. So this is what characterizes the tenor graph. So we can represent it in this way or in this way. This, I mean, in the representation in terms of parity check matrix implies a certain structure for the permutation. How can we decode a low-density parity check code? That's the standard way of do the decoding. Here I consider a simple single step. Remember, we have here we have 2 functional blocks, the repetition block and the parity check block. Very simple blocks, which means that very simple kind of calculations that have to be performed by each block when we do the single parity, I mean, when we do the sum product algorithm step. Okay, so the scheduling may be from left to right and from right to left. So we go from left to right, the calculation, compute all the messages going from left to right. Then we compute the message from right to left, and we keep on iterating until the a posteriori probability stabilizes to a almost constant value. Okay, these are the blocks representing the channel. So this nu sub I are the messages coming from our knowledge of the channel behavior. P density of Y sub I given X sub I. So once we know the channel and we observe the channel output, we have these messages. Okay, so let's compute, for example, this message. The message is corresponding to here, to this variable, going in the direction from the repetition nodes to the parity check node. This is very simple because we have seen that the message at the output of a repetition node is just the product of the messages entering the repetition node. So the message here will be the product of nu I times the product of all other messages. Well, we don't have this at the initial step because they come from the right. We are iterating, so we may decide that the initial values of these messages is just constant function. If we have binary value, the message will be 1 for value 0 and 1 for value 1. Okay, so we have this. The other step, once we have computed all this, we transfer the calculation on the other side of the permutation and we go in the other direction. So let's suppose that we want to compute the message corresponding to variable symbol 1. Okay, it's convenient to represent this message since are binary variable to normalize. We normalize them to make them in the form of probabilities. Okay, and we may call 1 minus P1 and P1 the two values. So we just normalize them in order to have numbers going from 0 to 1. We call them probabilities. So we need only to compute P1. Okay, and P1 in this case is easy to realize that since because of the simplicity of this node is equal to 1/2 plus 1/2 the product of the 1 minus 2PL, where PL are the corresponding messages entering the node. So you see that the kind of calculation to be performed is quite simple. Of course, there's a lot of them because if you want to have good performance for the code, we need a long block code. And a long block code also implies that we must have a large girth for the factor graph in order to have good convergence properties. And but the kind of calculation that had to be done in every step, you can see, is very simple. And it's also very simple to understand why we do this calculation. We do this calculation because each one of these two steps, calculation of this guy and calculation of this guy, are simply an implementation of the basic step of the sum product algorithm applied to these two simple functions, the repetition function and the parity check node function. Okay, so that's it. So that's all we need to know to decode a low-density parity check code. Of course, designing a low-density parity check code is not a trivial operation, and implemented this may not be a trivial operation, so in some cases we may need some approximation, but it's important to understand what the optimum algorithm for decoding is. That's very simple, as you can see. What's the performance of low-density parity check code is on a Gaussian channel. These are coded rate 1.4. This is the performance of a regular low-density parity check code. We also have irregular low-density parity check code. Irregular low-density parity check code are such that the number of ones in each row or the number of ones in each column are not exactly the same. So we may have some irregularity in the weight of the rows on the column. And of course, this provides us with an additional degree of freedom, and we may improve the performance. But we can compare the performance of this with the Shannon limit, and we see with corresponding to the same rate, 0.25, and we see that we are very close to the Shannon limit and around 1 point something dB. Okay. And this, we see that the block length is the blue and the magenta 16,000 and 64,000. So this is the order of magnitude of the block length that we need in order to have a good performance for this code. Turbo code. This is an example of a turbo code, a very good turbo code. We have here we have the two convolutional encoders, systematic convolutional encoder. We see that we send over the channel only the parity part, and the tenor graph, as we have seen before, is done like this, where the first block on the left representing, describing the convolutional code C1, this describes convolutional code C2, and this is the structure. Again, in most cases, C1 and C2 are the same code, and consequently, the operation of these blocks in the graph are the same on the left, on the right, and due to the periodic structure of the trellis of convolutional codes, each block here performs the same operation, which simplifies the design, of course. How can we do decoding of turbo codes? It's relatively simple. We go from left to right and from right to left. So we do the calculation of the mesh. What we need is the a posteriori probability associated with this variable, you know, the original, the data, the information data. And what we have to do is to go from, to splice this black dot with channel functions, so to observe the channel output corresponding to this symbol, and then we go from left to right and from right to left a number of times until we have convergence. So that, again, we don't have to reinvent the wheel to understand how a turbo decoder goes. We look at the tenor graph, we decide upon a schedule, which is typically from left to right and right to left, and then we do our decoding by doing single steps of the sum product algorithm or approximations thereof if the single step is too complex. Okay. We see that in this case we need a relatively simple convolutional code because we have to perform many times the calculation involved with this function. Okay? So we need a relatively simple trellis structure, otherwise the complexity of the calculation would be overwhelming. This is the performance of a turbo code. That's an interesting fact about turbo codes, is that they perform like this. This is the iteration order. If we do only one iteration, we get this performance. Then with two iterations, 4, 8, 16, we see that the performance improves with iteration. Of course, because for every iteration we refine, we improve our approximation of the a posteriori probability that we need for decoding every single variable in the code word. We also observe something that escaped originally the inventors of turbo code, the presence of a narrow floor. This is not, it's called narrow floor, but it's not technically a narrow floor, it's just a change of slope. So what we have here is that the error probability for a while remains constant for, almost constant for a low signal to noise ratio. It depends very little on the number of iterations. Then we have a waterfall region in which the probability falls down very quickly. And then we have this change of slope. This change of slope is due to the fact that once we have a very large signal-to-noise ratio, the error probability, have seen yesterday, depend on the minimum distance of the code. And turbo codes don't have a especially good minimum distance. Consequently, the error floor may they reflect a relatively poor performance. But we have a good performance in the waterfall region, and that's what really matters. So turbo code work well if the error probability falls in the waterfall area. They don't work well if we need a large value of EB or zero, very low value of error probability. It's always a value of error probability that yields this change of slope, in which case it's better to use a code that has a larger minimum distance. Let's try to understand the convergence properties of turbo codes. But first, let me just comment on performance of turbo codes. These are three turbo codes corresponding to rate 1/2, 1/3, and 1/4. These curves on the left are the Shannon limits. We cannot do anything better than these. And C corresponds to rate 1/2, B to rate 1/3, and A to rate 1/4. And this is the block length of 16,000 block length. And we see that we are less than 1 dB away from the optimum performance, so the best we can actually do. These are not the world record of coding, but anyway, this is what we can get with a relatively small block length. If you have a block length of millions, then you can get something better. Anyway, this is more realistic. This is a simulation curve showing what happens with block length 100,000 with number of iterations from 1, 2, 4, 8, and 16 iterations. This is what we get. You see that, especially at the beginning, the improvement in with number of iterations is considerable, and then the principle of diminishing returns holds in the sense that you increase the number of iterations and you improve very little the performance of the code. How can we understand the convergence property of turbo code? It's very difficult. Rüdiger Urbanke will tell you about this early next week. But anyway, the exact analysis is very difficult and not impossible. On the other hand, there is a technique that I'm going to describe in a minute called the exit chart techniques that from an engineering point of view works very well because it's an approximation, but it yields a lot of information about the convergence property. Remember that if you want to study the convergence property using analysis, you will never get there. If you use simulation, then it's very time-consuming because you have to do, in a practical circuit, you can do operation in parallel. If you have just a PC that doesn't allow for parallel computation, then you have to do the computation serially, and the calculation is very, very long and painful, especially if you want to get to probability of errors 10 to the minus 5, 10 to the minus 6. So it's maybe painful to design a code by just simulating one, change the parameter, simulating again, and so forth. So we need a tool that may not be the most sharp, the most refined tool, but it yields a lot of information about how to design and how to analyze a turbo code in terms of its convergence. I'm going to describe this. The technique is called the exit chart technique. The exit stands for extrinsic information transfer. And it describes the convergence of the iterative algorithm by showing how the probability density function of the extrinsic message or the messages exchange changes. Okay? And there is a fact, the experimental fact, that the extrinsic messages expressed as log likelihood ratio, I'll return on this in a moment, approach a Gaussian distribution. So with a Gaussian distribution, we need only two parameters, but there is something better than that. Mean and variance of this Gaussian distribution are linearly related. Okay? So we need only one parameter to to study the evolution of that Gaussian distribution. Well, to the extent that the distribution of the extrinsic message is actually a Gaussian distribution, which is approximately true, especially when the noise is not too small. I'll return on this. Extrinsic messages are, let's consider binary case for simplicity. Remember that, at least in the case of low-density peri-check code, we have seen that. There are two numbers. We can normalize this number so that their sum is equal to 1, and consequently we can present them as probability. And so we can define the ratio between this probability and the logarithm of that ratio. So we can represent every message as a logarithm of the ratio between the two probabilities, the two numbers of characterizing messages interpreted as probabilities. Okay, this log likelihood ratio approach a Gaussian distribution. So we can study the evolution of the algorithm by studying the evolution of this Gaussian distribution. Just to understand why we have this very simple calculation that shows how mean and variance are related, consider a transmission of binary antipodal signal on an additive wide Gaussian noise channel, x plus noise. So the probability density of y given x is the density of the noise with mean x. So we have a constant, and a relevant constant, e to minus y minus x, which is given, divided by 2 sigma square of the variance of the noise. If we compute the probability of y given that x is equal to plus 1 divided by the probability of y given that x is negative, take the logarithm, we get this, 2 over sigma z square x plus z. The appearance of this z here means that this quantity is conditionally Gaussian. So given x, lambda of I is Gaussian, is normal, with mean 2x divided by sigma z squared, and variance 4 over sigma z squared. So we see that mean and variance are really linearly related given x. So we can represent the evolution of this density by studying, for example, the mean and the variance. Well, it has been seen that it's more convenient, it's more engineering satisfactory and practically useful to describe the evolution of the density of E by showing the evolution of a quantity related to the density. And this is the mutual information between X and the likelihood ratio. Well, the likelihood ratio carries some information about X. Okay? The mutual information measure how much information lambda gives us about the true value of the symbol, of the code symbol. And this is the integral that expresses this mutual information. Okay, now let's return to the iterative algorithm. Remember, we have two blocks. This block represents the code, and this block represents the channel. Okay? Every step of the iterative algorithm consists of sending messages into the other block, having the other block compute new messages and getting them back. So we have messages going downward in one step and going upward in the further step. And we keep on transmitting these messages. Every set of messages, the messages going downward and messages going upward, carry some information. Okay? So there is an average information that these messages carry about the corresponding values of the symbols. So we can think of the step of the iteration as a change of the mutual information, the average mutual information, from the mutual information carried by symbol by message E to mutual information carried by symbol E prime. Okay, so we start with messages, certain amount of mutual information. Then we do one step of the sum product algorithm, and we get another mutual information, hopefully increasing. And then with another step, another mutual information, and so forth. So we study the evolution of this mutual information as the iteration proceeds. Exit charts are based on the transfer function of the block. And a transfer function that tells us how the mutual information, the average mutual information about these code symbols is changed from one iteration step to the next one. And we can evaluate this by doing by simulation. For example, this is what we have with convolutional code. This the mutual information at the input and mutual information at the output. So we see how mutual information changes from step to step for several convolutional code with different rates. And this is for turbo codes. If we have a turbo code, we see how the mutual information changes from step to step. Now, and this is for other simple code, repetition code, and so forth. These are examples of transfer functions. How do we use this? Okay. Let's focus for the moment on the two external curves, this one and this one. Okay. Let's suppose that one of them represents the transfer function of the lower block, and the other one represents the transfer function of the upper block. Now, when we do iteration from by computing messages that flow from one block to the other block and vice versa, what we do in this graph is to move along this staircase, along this blue staircase. Okay? So the message, we start with a, let's say, a mutual information of point 17, and we move to a mutual information point 25, and then another iteration brings the information to point 36, and so forth. And we keep on going until we reach this, this point. Well, if we could actually reach this point corresponds to a mutual information 1, which means that that the likelihood ratio carries all the information related to the variable, which means that we have no error. Actually, in this region, the exit chart is not accurate enough because we don't have enough noise to justify the assumption that the messages are Gaussian. So the exit chart work well in this area. This area tells us what happens in terms of convergence, because we see that in this case we have convergence after 1, 2, 3, 4, 5 double steps of iteration in the iterative decoding. And this is possible because we have this canyon between the two exit curves that is passed by the staircase. Consider another case that corresponds to the same set of codes, but a smaller signal-to-noise ratio, 0.6 dB of EB over N0. This corresponds to these two transfer functions. Okay? So we do the same iteration, we go up, up, etc., and we get stuck here simply because the canyon is not open. The two curves intersect each other. And consequently, we keep on iterating, and we discover that the error probability doesn't improve much. It doesn't improve almost nothing, simply because we cannot pass the canyon because the canyon is not open, it's closed. So this kind of exit chart is done by simulating the system separately, the one code, the other code, the upper block, the lower block. Okay? We derive the transfer function for certain values of signal-to-noise ratio. And then we observe the two curves and we see if there is a canyon open or closed. If it's closed, we don't have convergence. If it's open, if it's wide open, the convergence is fast. If it's very narrow, the convergence is slow. We can do even more than that. We can approximate, well, this shows that the exit chart analysis was correct. The blue curve corresponds to the higher value of signal-to-noise ratio, in which we have a convergence from iteration to iteration. The error probability decreases very quickly, and this corresponds to a case in which we don't have convergence. After a while, the error probability doesn't decrease in a relevant way, and we get stuck. We have no convergence. We can also superimpose to the exit chart the approximation of bit error rate curves, and consequently we can study the evolution of the error probability when we increase the number of iterations. So this is a very, very useful and very practical way of doing it, because it's simple. We do the simulation of the exit chart once for all, and then we study the convergence, and we discover that the convergence, if the convergence is fast or slow. Very, very useful. Okay, this concludes my discussion of coding on vector graph. The last topic that I'm going to cover in this short course is the topic of MIMO. And in particular, the space-time coding, that is coding for MIMO systems. So let me spend a few minutes describing what a MIMO system is, then I'll focus on space-time code, that is for code specifically designed for MIMO systems. The idea is to use, the idea of MIMO is to use more than one transmit antenna and at the same time more than one receive antenna. It's called MIMO for multiple input, multiple output. This is the standard block diagram of MIMO. We have a transmitter, a number of transmit antenna that I call T, a number of receive antenna that I call R, and in between we have a fading channel with path going from each transmit antenna and to each receive antenna. And just to give a very simple example of a MIMO, consider 2x2 MIMO, simple but by no means trivial. 2x2 MIMO, here we have two transmit antenna, two receive antenna, we have four paths, and we call H11, etc. the fading gains associated with each of the paths, and consequently what we observe at the output is the following. At the output of this antenna, we have a linear combination of the signals transmitted by antenna 1 and antenna 2 plus noise, and similar for the second antenna. We observe immediately what is the major problem of MIMO. The major problem comes from the fact that what we receive here, what we observe, is a linear combination of the signal transmitted by antennas 1 and 2. So we have to separate signal X1 and X2 from our observation. A naive observation could be at this point, as okay, we have a system of two equations and two unknowns. we observe Y1 and Y2, we assume that the channel state information, that is, the values of H, are known at the receiver, so we solve a linear system of two equations with two unknowns. That's naive, and in some cases it may even work, but in practice it doesn't, essentially because it may not be the best solution to solve a system of linear equations in the standard way when we are in the presence of noise. If it were not for the noise, and we could solve the system of linear equations and get the values of x1 and x2, but the noise makes things impractical, as we shall see in detail. Okay, this system can also be written in a matrix form. So we have here we have a vector of a received signal, a matrix representing the fading channel effect, a vector representing the transmitted signal, and a vector representing the noise. So the general version of a input-output relationship for a MIMO system given by vector y with dimension r, because we assume to have r receive antennas, equal to h, the channel matrix, r times t, we assume to have t transmit antennas, multiplied by the transmitted vector plus noise. Okay, that's the general expression. You may remember the general expression for a fading channel, for the scalar fading channel that we have considered yesterday, with y equal to rx plus n. So the formula is the same, except that now we are dealing with vectors and matrices rather than with scalars. But we shall see in a moment that when it comes to maximum likelihood decoding and so forth, the equations are formally the same as in the scalar case, except that we are dealing with matrices rather than vectors, and vectors rather than scalars. What can we expect? I mean, from a MIMO system, what kind of upsides there are, and what kind of downsides there are if we use MIMO. Well, let's consider two limiting cases. First, a limiting case is where we use the T transmit antennas to send to the channel the same signal. So we have the same signal x1 transmitted by all antennas. What happens? Remember, in this channel, we have T times R fading paths, because there are T transmit antenna, R receive antenna, and all transmit antenna are connected to all receive antenna. That means that at the end of the transmission of this signal traverses this many paths, T times R. So x1, we can find x1 on each one of these paths. Now, under the assumption that the paths are independent, we have a diversity gain for this, because we observe the same signal through T times R independent channels. And this is called the diversity, and the diversity generates the diversity gain that is proportional to T times R, because we get the same information through a number of independent paths. And we can take advantage of this independence by using maximum ratio combining, if you're familiar with it, or any kind of combining, in order to improve our performance. We have a diversity gain T times R. So that's the one limiting case. We transmit the same signal through the whole set of transmit antennas. The other possible limiting case occurs when we transmit T different, independent signal through the antennas. What do we have here? Well, we have first the fact that for every channel used, that is for every time instant in which we transmit, the rate has increased because we are transmitting T signals rather than only one. But on the other hand, each signal traverses only R independent path. Okay? So the rate gain is not the, R times T as before. The diversity gain is not R times T as before, but only R. So in the previous case, we have no rate gain. We transmit one signal, x1, per channel use. And we have diversity gain T times R, because this signal traverses T times R independent paths. In this case, if we send independent signal from all antennas, We have a rate gain t because for every channel used we can transmit t signals rather than one. But on the other hand, we have a diversity only r because each signal traverses only r independent path. X1 traverses only one path per receive antenna. So we see that we have two limiting cases, either a maximum diversity gain but a minimum rate gain, or a large rate gain, a maximum rate gain, but a minimum diversity gain. So, can we consider intermediate situation in which we have some diversity gain and some rate gain? Yes, there is a possibility of having a trade-off between a rate gain and diversity gain, and actually the design of a MIMO system is based on the trade-off. And we can do it by using coding to introduce some correlation among transmitted symbols. In the first limiting case, the signal were all the same. In the second limiting case, the signal were independent. In between, we can consider some correlation between signals. And this is obtained by using coding. This is called space-time code for a reason that will be apparent in a minute. The noise, in the calculation, the noise model is Gaussian noise, assumed to be independent across antennas and across time. So this is called spatially and temporally white. How about the channel model? Well, there are many. The one that gave rise to the richest literature is called the rich scattering model, in which the entries of the matrix H that represent the channel are assumed to be independent Gaussian random variables with mean zero and independent real imaginary paths. So everything is independent. Everything you can think of is independent there. This is called a Rayleigh model or a rich scattering model. This is valid model once we have a propagation situation in which there's a lot of reflections and the space in between antenna is large enough so that we can assume that there is no correlation among the antenna input and output. The other model assumes that there is some correlation among antennas, and so the entries of H are still Gaussian random variable but correlated. Or we may have a Ricean channel in which we have independent Gaussian variable but the mean is non-zero, or a keyhole channel. In some cases we have propagation, indoor propagation through the hallway or a tunnel, in which it happens that the entries of H are still uncorrelated but the matrix H is rank 1. These are all limiting cases, but all the calculations that I'm going to describe today are based on a rich scattering model. I want just you to know that there are several other possible models that lead to different calculations. So, yes?
How can the entries be uncorrelated and the rank be 1? That means that they're all linear independent.
Yeah, uncorrelated doesn't mean independent, and consequently you might have any rank for the matrix. That's what happens. I can discuss that later on. It's not especially mathematically sophisticated, but it's a mathematical trick. Okay. So the general problem of MIMO reception is that we have a received signal. We have seen it before in the case of a 2x2 antenna. A received signal, a linear combination of a transmitted signal, and we want to recover the individual transmitted signal. While multiple receive antennas have been in use for many years, for many decades, the use of multiple transmit antennas came into play only a few years ago, just because of the difficulty of separating this signal. The first practical scheme that was very well accepted and actually found its way through a number of standards is called Alamuti scheme. I will show you how Alamuti scheme is a very simple, we can call it a coding scheme if we want, scheme that allows the separation of signal X1 and X2 in the case of a 2x2 antennas with a very simple procedure. Okay? The idea is the following. we have two symbols to transmit, x1 and x2. So the coding scheme consists of the following. At first time instant, we transmit x1 from antenna 1 and x2 from antenna 2. In the second time instant, we transmit minus x2 star. x2 are a complex symbol, so a star means complex conjugate, and x1 star, like this. So this is what we transmit at time instant 1, and this is what we transmit at time instant 2. Let's assume that we have just one receive antenna, and H1 and H2 are the fading gain of the two. Okay. What we receive at the single receive antenna is a linear combination. At time 1, we receive a linear combination of x1 and x2 with coefficient h1 and x2 that we assume to be known at the receiver. The next time instant, assuming that the channel doesn't change quickly, so quickly that the transfer function of the channel changes from one instant to the next, we have a linear combination of x1 star and x2 star like this. So this is what we observe. Point is, how can we derive x1 and x2 from these two equations without solving the system? We do the following. We have a combiner here, the block called a combiner, that operates like this. It takes a linear combination of the observation at time 1 and at time 2. So it does h1 star y1 plus h2 y2 star and h2 star y1 minus h1 y2 star. If we do the calculation that leads to x1 tilde and x2 tilde, you discover that x1 tilde is equal to x1 multiplied by a certain quantity that I'm going to comment upon in a moment, plus noise. And x tilde 2 is equal to the same term that multiply x2 plus noise. That means that we have separated x1 and x2. The calculation of the first part of the calculation of the combiner generates something that is proportional to x1 plus noise. The other one proportional to x2 plus noise. So we can send x1 tilde and x2 tilde to a detector, to a demodulator, and we have the detection of the symbols x1 and x2. You see that the operation is just a linear operation, because the combiner is a linear, there's a linear operation, and this is what we obtain. In addition, we see that x1 is multiplied by magnitude square of h1 plus magnitude square of h2. This means that we are taking advantage of both paths, we see, path h1 and h2. We combine them together, and we compensate for the potential weakness of one of them by adding the contribution of the other path. We say that we have diversity 2, because we take advantage of the fact that we have two independent paths here. And we increase the factor multiplying x1 by taking into account that fact that we receive x1 from two different paths. This is a very interesting result, so because we separate x1 and x2, and it can be shown that we have exactly the same performance as if we had one transmit antenna and two receive antenna with maximum ratio combined, which is the optimum combining of signals received through two receive antennas. This is important because we can see that we have, with two transmit and one receive antenna, we can have the same performance as with one transmit and two receive antennas. At first sight, it may look like an obvious thing, but it's not, because in some cases it's easy to have more than one antenna. For example, in a base station, it's easy to have more than one antenna. But in a mobile receiver, in a cell phone, it's difficult to have more than one antenna. And consequently, I have the same advantage of a multiple antenna at the receiver by putting multiple antenna at the transmitter in the part of the system where it's easier to generate, to use more than one antenna. So that's the reason why Alamuti scheme is so popular. We have no rate gain, actually, because we are transmitting two signals in two different channel uses. We need two timings. It's not mine. Huh? Okay. We need two time instants to transmit two signals. So we don't have any rate gain. We have diversity 2 because each signal traverses two independently faded channels, and we can exchange receiver diversity for transmit diversity. So that, as I said before, this is very convenient when it's not possible to achieve receive diversity. This is the simplest possible scheme, Alamuti scheme. We can also generate an Alamuti scheme with two transmit antennas and a different number of receive antennas, for example, 2. The transmission scheme is exactly the same as before. At time 1, we transmit x1 and x2. At time 2, we transmit minus x2 star and x1 star. And then we combine linearly the signal received by the two antennas in two adjacent time instants. For example, in this case, the combiner generates a linear combination of the y's received at different time instants by different antennas. And the result is, as before, the result of the combination is something proportional to x1 and proportional to x2. In this case, we see that we have diversity 4 because we combine together the gain of the 4 paths traversed by each signal. Even in this case, we have the same performance of a single input, multiple output system with 1 transmit antenna and 4 receive antennas. So we can combine, we can distribute the number of antennas to the transmitter or to the receiver according to our convenience and get essentially the performance of a system with 2 by 2 or 1 by 4 or 4 by 1. With t equal to 2, Alamuti scheme can be generalized to every conceivable value of a number of receive antennas. The point is that Alamuti scheme that perform this well do not exist if we want to use more than 2 transmit antennas. In fact, it can be proved that if we want to have the simplicity of the Alamuti scheme, I mean, linear combination that separates the system, to separate the signals, then we have to give up something in terms of rate. In fact, if we want to have an Alamuti type scheme with t greater than 2, more than 2 transmit antennas, then the rate drops to no more than 0.75 signals per channel used. These are called orthogonal design. So you may use an orthogonal design with t greater than 2 to exploit the simplicity, the conceptual practical simplicity of the Alamuti scheme, but the rate will drop to 0.75 or less. Now, how can we do maximum likelihood reception? Let me just show you a couple of slides here before taking a break. Do maximum likelihood reception exactly in the same, formally in the same way as we do it for scalar case. Remember, in the scalar case, we have to compare y with the faded version of all possible transmitted signals. We assume that the value of the fading random variable is known at the receiver, so we had to compute a minimum distance between what we receive and what we have potentially transmitted over a channel whose transfer function is the known value of matrix H. Okay, that's formally okay. If we expand this norm, we discover that the calculation depends, the number of calculations is proportional to the number of receive antennas and to the number of transmit antennas. In addition, if we minimize this quantity, this distance, with respect to all possible values of the transmitted vector x in using a brute force approach, we have to list all values of the vector. And the values of the vector, the number of values of the vector may be considerably large, especially if we have a large number of antennas. Suppose that we are considering a quaternary constellation and we have t antennas, then we have how many possible values of x we have. We have 4 values for component and we have t component. Consequently, we have 4 to the t possible values of the vector x. Consequently, the complexity of maximum likelihood reception increases exponentially with the number of bits in the constellation and with the number of antennas. So it may become quickly impractical. Okay? 2 by 2 may be practical, but 4 by 4 or 16 by 16 will definitely not be practical. Let me show you an example, a simple example for a 2 by 2 system. This is the value of the distance, so we have to compute all possible values of the distance for all possible values of x1 and x2. And notice that x1 and x2 are not separated. If we are not using Alamuti scheme, x1 and x2 are not separated. So we have a function of two variables, x1 and x2, that we have to minimize in this case. So in general, the minimization requires to compute the calculation of m to the t value of the norm, where m is the size of the constellation, the elementary constellation, and t is the number of transmit antennas. So the implementation of the maximum likelihood receiver, as I mentioned before, is restricted to small values of m and t. Think, for example, of Ymax. Ymax allows a constellation of up to 64 QAM. And for two antennas will mean a huge number of calculations per symbol, something that does not allow, may not allow the maximum likelihood reception. So we may have to resort to simpler techniques. I think it's a good time to stop here and take a 20-minute break before computing the performance of the maximum likelihood receiver, showing how you can simplify the receiver and a few space-time coding schemes.
Just before we leave, as some of you know, we have a long-standing tradition of taking a picture with